Ionic compounds. We're going to learn how to write their formulas and how to name them. But first of all, we'll talk about them a little bit. Ionic compounds are very common in the Earth's crust. We call them minerals. They also show up in the food that we eat. Here's two things that you might ingest. This is Morton's light salt. Light salt is a mixture of sodium chloride and potassium chloride. So you get less sodium when you eat it, but it still tastes salty. And Tums is an antacid, and the active ingredient in there is calcium carbonate, which is also an ionic compound. We recognize this because calcium is a metal and carbon and oxygen are nonmetals. Here's an example of a couple of minerals that you might find if you were digging in the dirt. On the left is calcite. This is also a form of calcium carbonate, but I wouldn't recommend eating that if you have indigestion. It's not going to help you out very much. Calcium carbonate can come in many, many different forms. And on the right is an example of trona, which is a crystalline form of this big old mess of a formula. Ionic compounds tend to be very stable because the ionic bonds that hold them together are really strong. You've got positive and negative charges being attracted to each other, and not just in one direction. Within that lattice, a cation is attracted to anions in multiple directions, and so it tends to be very, very stable. We need to learn how to write the formulas for ionic compounds. So here are the steps. First of all, you need to write the symbol for the metal cation with its charge. Charges are really important in ionic compounds. And then you follow that by the symbol for the nonmetal with its charge. You need to first write down the formulas for the ions with their charges, because the charges are going to tell you how many of each are in a compound, because they have to be charge neutral. We're going to adjust subscripts on each cation and anion to balance the overall charge. The number of positive charges has to equal the number of negative charges. And then we're going to check that the sum of the charges of the cations actually equals the sum of the charges of the anions. So for those of you who like written sets of instructions, there's your instructions. Some other thoughts. Important to remember that ionic compounds always have positive and negative ions. The first element is usually a metal. There are exceptions. I think the only one we'll see in this class is the ammonium ion, NH4+. This is a polyatomic ion that has a positive charge. That's a cation. So if you see a formula that starts with NH4, it's an ionic compound even though it may have no metal ions in it. In any chemical formula, the sum of the positive charges and negative charges must be equal. And the formulas for ionic compounds represent the smallest whole number ratios of ions. So if you end up with something like Na2Cl2, you need to simplify that. Otherwise, we know what you mean, but it looks goofy. It's like when my second child was 2, he referred to a cash register as a dollar biller. We knew what he meant, but it sounds silly, right? It's not proper English. So if you say Na2Cl2, it's like calling a cash register a dollar biller. I know what you mean, but you sound ridiculous, especially at your ages. Let's do some examples. Write the formula for the ionic compound that forms between potassium and sulfur. So first thing is we need to write the formulas for these ions with their charges. Well, what is the element symbol for potassium? K. What charge does a potassium ion have? +1. Okay, that's not magic. That's on the periodic table. Potassium is in group 1. Group 1 metals form +1 ions. Sulfur has the symbol what? S. And what charge does a sulfur ion have? 2-. We look at the periodic table, and we start in the noble gas column with 0, and we count backwards till we get to sulfur. -1, -2. Okay? That's an important thing to know how to do. We covered that in the previous chapter. Now that we have these formulas with their correct charges, we have to figure out how to combine these so those charges add up to 0. There's different ways to think about this. If you're good with math, you're looking for the least common multiple, I think is what they call it in math. Here we've got a 1 and a 2, and we're trying to find the smallest ratio, and so we need a K2S. Okay, some people can do that easy peasy. Other people are like, what on earth did you just do? So I'll show you a picture method and kind of a hack cheat method. So picture method, if we just kind of total up down here, from the sulfur we have a -1 charge, and from the potassium we have a -2, and from potassium we have +1. Those are not the same. We want +2, -2, +3, -3, something like that. We cannot make this number any smaller, but we could add to this one, and we could do that by putting in another potassium ion. That would give us +2. That's what we're looking for. How many of these do we need so that we can have these charges be the same but opposite? Now I look at this, I've got 2 potassium, so I write K2. And I've got 1 sulfur, so I just write the symbol for sulfur. So that's what I call the visual method. So let's look at that hack method. Hack method is called crisscross, and students like it. It works most of the time, but it'll occasionally get you in trouble. So first thing with the crisscross method is to look at these charges and ask yourself, are they the same? No, they're not. If they're the same, all you have to do is shove the 2 ions together and you're done. Don't crisscross if it's +1, -1, +2, -2. These aren't the same. So then we're going to take this charge and it's going to become the subscript for the other element. So I'm going to take this unwritten 1, and that's going to become an unwritten 1 for the sulfur. And I'm going to take this 2, and that's going to become the 2 for the potassium. And I get K2S. Works most of the time. So whichever method you like, there's 3 of them, at least. Any questions? Okay, let's do aluminum and nitrogen. First thing is formulas of ions with charges. I write it with a script L, so it doesn't look like a 1 or a capital I. What charge does aluminum have as an ion? 3+. Because it's in group 3A. 1A has charge of 1+, 2A, charge of 2+, metals in group 3A, 3+. How about nitrogen? 3-. Again, counting backwards on the periodic table. Now we look at these 2 guys. We've got +3 and -3. If we just shove them together, they're going to add up to 0, and we're good. So this is A, L, N. Done. Any questions? I need to point out to you that capital letters and lowercase letters are really, really important in writing chemical symbols, because CO is carbon monoxide and C(o) is cobalt. Very, very different. Capital O, lowercase o, the only difference is size. So some of you have very messy handwriting. I completely understand that. But when you write your chemical formulas, slow down and do them carefully so people can read and understand. Because an error like this could kill somebody, right? It could kill somebody. The other thing you need to watch out for is using large lowercase letters. That is not a capital A, it's a giant lowercase a. People have different handwriting styles. Sometimes people write tin like this. They like to write in all caps. There's small ones and big ones, right? Not when you're doing formulas. You all know the correct way to do it. The rest of your handwriting, I don't care. But when you're writing chemical formulas, this is not correct, and this is not correct. Okay, that's just wrong. Any questions? Writing formulas for ionic compounds. What about naming them? Some compounds have common names. These are kind of like nicknames. They're just like seemingly arbitrary names. But chemists have also developed a system of systematic names for different compounds. And this generally is called nomenclature, and it's usually not a favorite topic of students. If you take the time to understand the rules, it actually makes a lot of sense, and it makes much more sense than conjugating verbs in the English language or even just spelling words. It's much more consistent than that. And you know, if everybody had a nickname, you just have to flat out memorize nicknames for everyone, right? If every compound had a common name and that's all we used, which is how things started out, there's no clues in the name as to the formula. In the systematic naming, the name gives you major clues about the formula for the compound. So the first thing we have to do when we're naming a compound is to identify what kind of compound we have, because there are different systems of naming for different classes. Just like historically the Swedes named their children and passed last names on in a different way than Americans did, what they did is they took the father's first name and added the word son, and that became the last name for the child. So if your dad's name was Anders, and you were a guy, then your last name is Anders' son, because you're the son of Anders. And if you're his daughter, your last name would be Anders' daughter, D-O-T-T-E-R. Kind of cool. But then every generation has a different last name, and the boys and the girls have different last names. And so kind of confusing maybe, but that's how they did it. In the United States, generally the father's last name is passed on to the children. So it's a different system. You understand the system and you just go with it. So ionic compounds have one system, molecular compounds have another system, and organic compounds have a different system. So we have to identify. We've already gone over this, but we're looking for metals and nonmetals. If you have a metal and a nonmetal, it's an ionic compound. What's the one exception we've talked about? Ammonium. So if you had something like ammonium nitrate, nice little compound. We look at that, it doesn't have any metals in it. But we see NH4 and we know it's an ionic compound. So all of these, except for this one, have a metal and some nonmetals. Those are ionic compounds. You identify it as ionic and then you can use the ionic rules. We can group ionic compounds into two categories. I think these categories are a little dumb, but I'll go over them because your book uses them. So we can have compounds containing a metal that only forms one kind of ion, or we can have metals that have different ions. So sodium always forms a +1 ion. Iron is sometimes +2 and sometimes +3. So iron falls into this second category. These are metals that form one cation. There's a nice list of them here. There's the element symbol. There's the ion's formula with the charge. Here's the name of the ion and the group number. These are the American usage group numbers. These guys always form the same ion. Most of them are predictable by looking at the periodic table. The couple of exceptions here where we don't have charge being equal to group number are these three at the end: zinc, scandium, and silver. Scandium we're not going to run into very much at all, but zinc and silver are pretty important. The names for the ions are the same as the names for the elements. So this guy, Li+, the name of the element is lithium, the name of the ion is lithium. Easy. Then there's metals that can form more than one cation. Here are some of them. Pretty much every one except the ones on the previous table could form more than one ion. These are just some of the more common ones. So, for example, chromium can be +2 or +3. Copper can be +1 or +2. So in the name of the ion, we have to indicate which ion we are talking about. The old system used suffixes, us and ik. And I'm telling you about this just so you know that this exists. So if it comes up and you see, plummus chloride, you're like, what on earth? Well, plumum is the Latin name for lead. Plummus indicates which of the two common lead ions it is. But there's no clue in the us-ik about, is it +2, +3, +4, what is it? So I'm not going to make you memorize these. You just need to know they exist. So if you came up with, ferrous oxide or something, look it up. I don't remember what they are. I don't expect you guys to memorize stuff that I don't remember, because I do this all the time, right? I don't use that system. This is the stock system, which is what we use. This is the accepted system. This is like a holdover from the past. So this system makes so much more sense. The Cr2+ is called chromium with a Roman numeral 2. The Roman numeral tells us the charge. And Cr3+ is chromium 3, Roman numeral 3. So the charge is given as a Roman numeral after the element's name. We don't put Roman numerals on the other ones, like silver or lithium or sodium, because we don't need it. We don't want to write more stuff than we have to. So if we don't need it, we're not going to write the Roman numerals. So, Mrs. K's tricks. So, what about zinc and silver? Those guys, instead of just flat out remembering them, I prefer to look at the periodic table. And so here's group 3A. These guys are going to be +3. TL, we're just not going to run into him at all, so we don't have to worry about him. But here's aluminum, +3. And this forms this little triangle. It's not really the Bermuda Triangle, but it's this charged triangle. Aluminum, zinc, and silver, those are the ones you really have to have down. Aluminum is +3 because it's in group 3A. And then I imagine going down the stairs. So aluminum and down one is, that's +3, down one is +2, down another one is +1. You need to know that zinc is +2 and silver is +1. These also correspond to the 1B and 2B, but be careful with that because copper is not always +1. And gold and mercury do not follow that pattern. So I prefer to think of it as aluminum is +3, let's go down the stairs, 3, 2, 1. So if it's in group 1A, 2A, 3A, zinc or silver, no Roman numeral. Any other metal needs a Roman numeral when it forms an ion. And I'll repeat that a lot. Group 1A, 2A, 3A, zinc or silver. Those are the ones that do not need a Roman numeral. Everybody else does. What about the anions? Monoatomic anions. Just a single atom. These are all going to be nonmetals. And we learned about their charges and how we can predict them from the periodic table. What about the names? The names are formed from the element name. We take the ending off and we change it to "ide." So fluorine becomes fluoride. Iodine becomes iodide. Oxygen becomes oxide. Now, you'll notice that it's not always strictly just taking off the end. It's not oxyide. The Y disappeared as well. On nitrogen, the OG also disappeared. But generally, you take the element's name and you change the ending. And so those are names of the monatomic ions. So we're going to learn to name binary ionic compounds. What does the word binary tell us? 2. Binary means 2. So a binary ionic compound is composed of exactly 2 elements. 1 cation, 1 anion. And so the name is just a first name, the name of the cation plus the name of the anion. A lot like the normal convention for humans. We typically go by a first name and a last name. There's always a few exceptions, like Cher, just one name. And some people go with a middle name as well. But that's the pattern for most. So if we look at KCl, we're going to separate it into its ions. We're going to look at the K and the Cl, and we're going to name them separately and then list them. The metal goes first, the nonmetal goes second. Why? Because we decided on a wedding invitation, is it Mr. and Mrs. or Mrs. and Mr.? John Smith. It's always Mr. and Mrs. Why? Because that's how we've always done it, right? Now, you know, if you're really up into equality and stuff, you're like, well, yeah, but it's not really implying anything about the value or the relative importance of the two people. Somebody has to go first, right? And so we just decided. So here, the metal goes first, the nonmetal goes second. And I tend to think of the metals as being masculine and the nonmetals as being non-masculine or feminine. So if that helps at all, it's guy, girl. Potassium chloride. Potassium is in group 1A. It always forms a +1 ion, so it doesn't need a Roman numeral. We don't want to write extra junk. So potassium. Chlorine, we change the ending to chloride. We put the two names together. It's not a proper noun. We don't capitalize it. But there is a space between the two words. CaO. Well, this is the element calcium. Calcium is in group 2A. It always forms a +2 ion. Doesn't need a Roman numeral. Oxygen the name is oxide. And so we just put the two names, calcium and oxide. They're in the same order as the letters are in the formula. Here we go. So examples. Name this compound, Ag3N. Well, what's the nimble? I don't know where that came from. What's the name of Ag? Silver. Does silver form more than one ion? No. Groups 1A, 2A, 3A, zinc, or silver. No Roman numerals. Okay, so that's the name of the Ag3 part. We don't need to specify the 3 in any way. Charges take care of that. And what's the name of nitrogen as an ion? Nitride. So this is silver nitride. Nomenclature is not a place to be creative. Okay, there are other places in this class you can be creative, but not when you're naming compounds. The reason we don't need to indicate this 3 in the name is because of the charges on these ions. Silver, from the periodic table, we know is Ag+, and nitrogen, nitride, is in 3-. The charges give us the information to write the formula. So we can go from this name, silver nitride, to that formula without needing, trisilver nitride or anything funky like that. What about rubidium sulfide? What's the formula for that? Rubidium is Rb, and what charge does it have? +1. Another thing I forgot to point out, here's another example of chemists avoiding the number 1. This is a +1 charge, but we don't write the 1. It's just plus. And then when we write a charge that is different than 1, we write the number and it's followed by the sign. This is different than math, and I think it was intentional. We don't want these to look like they're exponents, because if we had a n to the -3, that would look like a variable raised to the -3 power. So we reverse the sign in the number so it doesn't look like that. And we always write the sign even if it's positive, and math people don't do that. So there's rubidium. What's the charge on sulfide? 2 minus. So to put these together, we need 2 rubidiums to balance the charge on the sulfur. Any questions? It's one of those things you have to practice to get. Well, what if you have one of those other metals that forms more than one ion? You're still going to put the name of the cation and the name of the anion. But now the name of the cation includes the charge in Roman numerals. If we're looking at the formula and writing the name, we sometimes have to figure out what the charge on that ion is, and we do that by inference, by looking at the charge on the anion and the relative numbers, and we'll do an example of that. Let's look at CrBr3. It kind of has a nice ring to it. How would we name this? Well, we have to identify the 2 ions that are present and then give them their names. We're going to name the Cr first and then the Br. So, what is the element name for Cr? Chromium. And now you ask yourself, is it in groups 1A, 2A, 3A, zinc, or silver? No, it's not. That means it needs a Roman numeral. How do we tell what the Roman numeral is? Well, we don't know yet. Put the parentheses in. There's no space between chromium and the parentheses. Leave space for the Roman numeral. We'll figure it out in a minute. What's the name of Br? It's bromide. Bromine as an ion, bromide. So we've got chromium, blank, bromide. Now we have to figure out what the Roman numeral is. We do this by looking at the charge on the anion and the relative numbers. I'll do it down here. So here we have chromium. We don't know what the charge is. And we've got bromide. What's the charge on that? -1. So minus. How many bromides are there? There's 3. So what's the total negative charge? -3. The total positive charge has to equal the total negative charge, right? So the total positive charge must be +3. How many CRs in the formula? Just 1. So we have 1 CR. We need a total of +3 charge. That chromium must have all 3 of those charges. So the Roman numeral would be 3. 1, 2, 3. Chromium 3, bromide. Any questions? Let's name this compound FeS. Well, Fe is which element? Iron. Does it need a Roman numeral? Yes, it does. It's not in groups 1A, 2A, 3A, zinc, or silver. So I'm just going to save space for the Roman numeral and then go on to the nonmetal. Sulfur becomes sulfide. Now we have to figure out what that charge is. So we've got 1 iron and 1 sulfur. What's the charge on sulfide? 2 minus. You look at the periodic table, you start at the the noble gases, and come backwards. -1, -2. In this formula, there's 1 of each of these. Here we have a total of -2. We must have a total of +2. There's only 1 iron, so it must have the 2+. That's just a bad. Try that again. So it's iron 2 sulfide. Write the formula for ruthenium IV oxide. What is IV? 4. Because the Roman numerals go 1, 2, 3. And you're thinking, man, if they're just going to write a line for each number, you get to 15. That's going to be a lot of them, right? Well, 5 is V, just because that's what the Romans decided to do. And 4 is 1 less than 5. And so it's 1 before 5, and 6 is 1 after 5. Just be thankful you don't have to do long multiplication or anything with those numbers. That's why they used an abacus, because you can't do it. Anyway, so this is ruthenium 4. So that tells us, what's the symbol for ruthenium? Ru. Ru what? Ruthenium 4+. And oxygen, oxide has what charge? 2-. This is an example of where crisscross can get you in trouble. Because you look at these and you've got 4 and, oops, didn't mean to do that. 4 and 2, they're not the same, so you do crisscross and you get Ru2O4. What's wrong with that? It's not the lowest ratio, right? The lowest ratio is RuO2. Oh, this would be a fun compound. Are you okay? Chemists just, I don't know, we get really dorky about playing around with element symbols. It's just too fun. So if you're doing the crisscross thing, be careful, always look, is it the lowest ratio? If you're not doing the crisscross thing, you look at this and you say, well, this is 2, that's 4 and that's 2, so I must need 2 of these to balance that one, and you come up with this. If you don't get how to put those together and come up with the formula, please come and talk to me. I've got a whole bunch of ways to explain it, and I'm pretty sure I can help you see it. And once you see it, it's not tough. Any questions? Polyatomic ions in an ionic compound. Same pattern here. You name the cation, you name the anion. But now the anion is a little more complicated. It's not just changing the element name, changing the ending to "ide." So names and formulas of polyatomic ions have to be memorized. But see, you're ahead of the game because I already made you memorize those. If you didn't, you better do it now, okay? So an example, NaNO2. We name this according to its cation. The name of Na plus is sodium. The name of the polyatomic anion, NO2-, is nitrite. Why is it nitrite? Because we decided to call it that, okay? And so the name is sodium nitrite. What I want you to notice is in this class, ionic compounds are always 2 ions, a cation and an anion. We'll occasionally see a formula that has more than 2 cations or more than 2 anions, but I will not make you name those because that's beyond the scope of this class. They exist, but you don't have to learn how to name them. So everything that you are needing to name will have 2 ions, 1 cation, 1 anion. What happens is students will look at this, NaNO2, and they'll want to break it into 3 things. And they'll get creative and they'll say it's sodium nitrogen dioxide. No, it's not. 2. So you look at the first element, sodium, and then everything else is 1 ion. It's got a special name. So here are some common polyatomic ions. And I think all of these were on the list, and there were some other ones as well. But all of these are ones that you should have memorized. If you'll notice, there is only one that's positive, ammonium ion. All the rest of them are negative. And there are some patterns in here, and we'll look at them in a minute. Most of these, their names end in either ate or ite. There's a few exceptions. There's hydroxide. That's a very common one, very important. Peroxide. This is a polyatomic ion of oxygen, O2, 2-. Sometimes a little tricky to recognize. Cyanide, also doesn't end in ite or ate. Cn minus. But I think all the rest of them end in ate or ite. Yes?
What do you name those with the sodium? Would it be sodium nitrate or sodium nitrite?
It depends on whether it's NO2 or NO3.
NO3.
NO3 would be sodium nitrate, and sodium nitrite would be NO2. So details matter. Just like in an email address or in a Master in Chemistry course ID, details matter, right? You get one letter wrong, and it doesn't work. You get one letter or number wrong in a chemical formula, and you could change it from something beneficial to something very toxic. And so details are important. Most of those polyatomic ions have oxygen in them. Let's go back and look at that table really quick. Oxygen, 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 oxygen. This one doesn't, that one doesn't, but almost all of them have oxygen in them. Those are called oxyanions. They're anions containing oxygen. And they have, there is a pattern to their names. So there are some elements that form a series of oxyanions. Chlorine is an example, nitrogen, sulfur, phosphorus, they form a series. And so what I tell students to do is you memorize the 8. That's going to be the one, if there's 2 ions in this series, that's going to be the one with more oxygen atoms, and the one with fewer is going to have the ending ite. So here we have nitrate and nitrite. The only difference is the number of oxygens. The charge is the same, the number of nitrogens is the same, but this has 3 oxygens, that has 2 oxygens. Nitrate and nitrite. This is sulfate and sulfite. Here it's 4 and 3 oxygens. The charge is 2 minus. Ate and ite refer to relative numbers of oxygens. More than 2 ions in a series, and then we stick some prefixes in front. We've got hypo, which means less than or below, and per, meaning more than. So here we have perchlorate. Per means this has 1 more oxygen than chlorate does. Hypo means 1 less than. So this is hypochlorite. It's 1 less oxygen than chlorite. So you memorize this one, chlorate. Then you can apply prefixes and suffixes to generate the others. It's a difference of 1 in the oxygen. Chlorine and bromine are in the same element family. They're nonmetals, so I think of them as sisters. Sisters often have some things in common. You know, my children have a lot of things in common. You look at them and you can tell they belong together. They look like they were made with a cookie cutter. Chlorine and bromine follow the same pattern in their polyatomic ions. Bromate is BrO3 with a -1 charge. Chlorate is ClO3 with a -1 charge. So actually, if you memorize the formula for chlorate, it also works for bromate and iodate. Iodate is IO3, -1 charge. And then you apply the prefixes and the suffixes to form the others. So you memorize 1 ion, chlorate, and the pattern, and you can write names and formulas for 12 polyatomic ions. Okay, so another slide of my tricks. Memorize the 8s in this pattern. Remember that only the number of oxygen changes. So you memorize this guy. And per has 1 more. Think hyper. Hyperactive, more active, right? Extra energy, extra oxygen. Ite, that's the light version. Bud Light has 1/3 fewer calories than regular Bud, right? So this is the light version. It has 1 less oxygen. And then hypo. Hypo means below. Where does a hypodermic needle go? Below your dermis. It goes below the skin. Hypo means 1 less. And just so you're aware, this is upside down of how the textbook shows you. They show you hypochlorite on top and perchlorate on the bottom. But I think of more going up, and so that's how I think of it. Any questions? Okay, let's name some compounds. SnClO3-2. Now, we didn't talk about parentheses. What's up with that? If you have more than one polyatomic ion, it can get confusing. So we use parentheses, because if I wrote SnClO3-2, that looks like 1 chlorine and 32 oxygens. That's not what I meant. And we're also not going to do SnCl2O6, because now it's really hard to see what that polyatomic ion is. So we're not going to do either one of those. What we're going to do is we're going to put parentheses around the polyatomic ion and put on the outside how many of those that you have. Have any of you guys been to Costco? So at Costco, they sell a lot of things that are shrink wrapped together. You can't just buy one jar of Parmesan cheese, right? There's 2 of them, and they've got plastic around them. You go in and you want to buy a game system. You can't just buy the game system. It comes bundled with an extra controller and like 2 games or something. But I just want this part. No, you have to buy the whole thing, right? So the parentheses here are like the shrink wrap. The polyatomic ion is a bundle pack. It comes together. You can't have part of it. And so it's shrink wrapped together, and on the outside, we tell how many there are. If there's only one of them, we don't put the shrink wrap on it. We don't write the 1, because chemists don't like to write the number 1 unless they absolutely have to. So then it would just be, NaClO3. There's only 1 of those ions, and so we don't put the parentheses and the number on the outside. So naming this compound, we look at the first element. Is it a metal or a nonmetal? It's over here, kind of on the rightish side of the periodic table, but it's under that line. It's a metal. This is an ionic compound. Of course, the title of the slide tells us that too, but those things will not always be there. What's the name? Tin. That's one of those weird ones. Tin is the name we use now, but SN comes from stannum, which is the Latin name for tin. Okay, so tin, does it need a Roman numeral? Yes, it's not in groups 1A, 2A, 3A, zinc, or silver. So I'm going to leave space for that. And then this guy, 1 ion. It's got more than 1 element in it, so it's a polyatomic ion. It has a special name, and what is it? Chlorate. So that's chlorate. So tin something chlorate. Now we need to figure out what the charge is. Well, what's the charge on chlorate? -1. And we have 2 of those, right? And we've got the tin, and we're trying to figure out what's that. Well, if we have 2 of these guys, and they're each -1, that's a total of -2 charges. And there's only 1 tin, so it must be +2. So this is tin 2 chlorate. Any questions? Let's write the formula for cobalt 2 phosphate. Writing formulas, you write the ion symbols with their charges first. So what's the element symbol for cobalt? CO, lowercase o. And the charge on this ion, 2+. Periodic table doesn't help us because the charge on cobalt is not predictable from the periodic table. That's why we have the Roman numeral. That tells us the charge. It's not the number of them. It's not the subscript. It's the charge. Phosphate. What's the formula for phosphate ion? PO4, 3-. Flashcards. pack of index cards, if you haven't done it already, phosphate on one side, PO43 minus on the other. When you're stuck in traffic trying to find a parking spot, just flip through them. Then how do we put these two guys together? We're going to need parentheses. How many cobalts are going to be in the formula? 3. And then we're going to have 2 phosphates. So we need to put parentheses around the phosphate and put the number on the outside. I can look at 2 and 3 and see that those are both factors of 6, right? The smallest number I can get where both of those are factors is 6. So I need plus 6, so I need 3 of those, and I need minus 6, so I need 2 of those. Or you can do the crisscross thing, or you can draw pictures. You'll come up with the same thing. I was going to say something else, and it vanished. What was I going to say about that? Oh, in the formula for the compound, we do not show the charges. So we don't put 2 plus up here and 3 minus up there. For one thing, it gets crowded and really messy looking fast. Another thing, it's just not necessary. And we don't want to write stuff that isn't necessary. So don't do that. Any questions? Almost done here. Hydrated ionic compounds. Hydrates are weird and really cool too. Some ionic compounds will associate with a specific number of water molecules when they form crystals. And so the water is incorporated into the structure. So Epsom salts is an example of this. Epsom salts have this formula, MgSO4, so there's the ionic compound, and then a dot. This dot is just saying these are associated. That's not multiplication or anything. That's just these guys go together, 7 water molecules. So for each 1 formula unit of magnesium sulfate, you have 7 water molecules associated with it. So in the systematic name, what you do is you name the ionic compound, magnesium sulfate, and then you use a prefix, a numerical prefix, hepta for 7, and then the word hydrate for the water. So this is magnesium sulfate heptahydrate. COCl2.6H2O. This is cobalt 2 chloride hexahydrate. We're not going to use these a lot, but they'll pop up now and then. These are the prefixes. Sometimes there's half. You might ask, how does that work? But we'll just accept it at face value. So if there's half, we call it hemi. There's mono, di, tri, tetra, penta, hexa, hepta, and octa. And we're going to use these prefixes a lot, so you should learn them. So let's name these hydrates. What's this guy? CaSO4.12H2O. Calcium sulfate, hemihydrate. So calcium sulfate doesn't need a Roman numeral. And then this is hemi for half, hydrate. How about this guy? BaCl2,6H2O. Barium chloride. No Roman numeral because barium is in group 2. Barium chloride. And then for 6, we write hexahydrate. How about copper 2 sulfate hexahydrate? What would be the formula for that? Once you get experienced at this, you may not need to write down the formulas for the ions with their charges, but when you're first getting started, or you just want to make sure you're getting the answer right, always write it down. So copper 2 is Cu2+, and sulfate is SO4 2-. So we look at those plus 2, minus 2. We just need to put them together. So CuSO4 dot, hexa means 6, so large 6, H2O. So that's hydrates.